Welcome, everybody. I'm Sarah McAllister. I host these LOF&BE webinar series with Sam Manzello and Sayaka Suzuki. And I'm very happy to introduce today's speaker is Professor Guillermo Rein. I don't feel like he needs an introduction, but I'm going to give one anyway. So he is a professor of fire science at the Department of Mechanical Engineering at Imperial College London and the editor-in-chief of the journal Fire Technology. His research is centered on heat transfer, combustion, and fire. The purpose of this work is to reduce the worldwide burden of accidental fires and protect people, their property, and the environment. His research portfolio is ample, but over the last 15 years, he is known in 3 areas: how polymers and wood ignite so we can avoid fires from starting, how engineers can design better structures that resist fire, and finally, how wildfires spread and how to fight them. He leads the research group at Imperial Haze Lab, but he was born in Madrid and went to UC Berkeley with me, and where he got his PhD in 2005. He joined Imperial College in 2012 from University of Edinburgh. So with that, I'm going to let Guillermo get started and take it away.
Thank you. Thank you, Sarah, for the introduction, and thank you for the invitation to Sarah and to Sayaka and to Sam. I'm happy to be giving this LOF&BE webinar. It's London here, so it's late. You will see that I will not raise my voice much, although typically I always raise my voice. I just don't want to wake up the kids. And if you see that suddenly I go quiet and turn the camera off because one of the kids is asking for something, but we are not expecting them today. So I would like to tell you a few things that we've been working on in the last few years on the topic of smoldering wildfires in particular. I've given the name to this seminar of a very important message for me, that smoldering is very often the beginning and also the end of flames. And I'll be addressing the meaning of this title in the talk today. A little bit of an overview of what I'm going to do is I'm going to tell you what smoldering is. I'm going to try to convince you of the important points that smoldering brings into wildfires and how it starts, how it spreads, and how it emits. I would also actually wrap up the second half with the 4 top challenges that we have seen of research in smoldering wildfires. The challenges have been addressed gradually, but they remain the hot topics where there is more need of attention. Most of the talk today is based on some of the chapters that I've been writing over the last several years. There is a chapter in the Handbook of Fire Protection Engineers, and also there is another chapter in a book by Claire Belcher. And you can always access this, and as a good academic, they're all open access, and if you cannot find an open access, you can ask me. So I would like to start talking about smoldering fires with the largest fire that North Carolina has in record. This fire is called the Evans Fire, happened in the summer of 2008, and it happened after a very intense drought that they have. And it was mostly a smoldering fire. It started with flames. The flames were stopped within a few days, but then the smoldering of the flammable soil, peat, the peat next to the coast of North Carolina, burned for several months. It led to an absolute massive amount of emissions. You see that satellite image over there of the white plume coming from the location of the fire. That plume there is a big plume, but it's not larger than the plumes that we are seeing, for example, these days in California. So it's not the size per se, is that plume was there not just for a week, but it was there for 2 months and a half, 3 months. And so when you're taking that into account, you can already see that when a fire smolders, consuming the soil, which is carbon rich, it ends up being a massive amount of fuel that is consumed because soil is much more dense than the vegetation that we have on the surface. It was very expensive to suppress this fire. It was one of the very rare cases of a large smoldering fire that was suppressed. It meant 20 million in suppression cost. The fire brigades had to be working there for weeks continuously, and they actually even diverted water from rivers and from the coast into re-wetting the wetlands. That's how we actually stop it. They brought so much water that the water table went up and the water table stopped the smoldering. You can see this image over here. It's an image that I use very often. This is a tree in the Evans Road. You can see that this tree itself is not dead, not at the moment of the photo, So this tree was not killed because of heat or because of the flames, and not of the smoke either. This tree is dead now, and it died a few weeks afterwards because it lost about a meter of soil all around its root system, and that's what actually killed not this tree but hundreds and hundreds of trees in the neighborhood of this fire. The Evans fire was not just a one-off. It was a one-off maybe in 2008 in North Carolina, but these type of fires happen with some frequency worldwide. The most famous ones are the ones that happen in Southeast Asia, in particular in the island of Borneo or other islands in the archipelago of Indonesia. This is the fire that happened in 1997. It's probably the first time that a smoldering wildfire made it into the news. Unfortunately, they didn't use the name smoldering, but when you look into what was burning, what was the peat, the soil, you realize that it was a smoldering. The cloud of smoke that it produced, particles in particular, was so large after many weeks of burning that it actually crossed into different countries. It reached China in the north of Indonesia, and it reached Australia in the south. And there were international complaints of what is now called trans-border pollution events, which get into politics and diplomacy, and is the highest probably level of complexity dealing with fires that go across, which consequences go across borders. Looking into media, we can see that the smoldering happens with different names all around the world in different years. We were very interested to see, for example, that Moscow and Siberia and St. Petersburg were surrounded in haze clouds from the peatlands burning around these cities. Which is a different type of wild urban interface fire, which is major cities, major urban centers were surrounded by smoke for weeks, creating acute emergency problems. It happens in the United States. It has happened in Southeast Asia. At this point, I want to use the word haze. Haze is when the atmosphere is hazy, means that there is a lot of particles, and smoldering produces haze. In the particles emitted from smoldering, they are not buoyant enough to go up high in the atmosphere, so they accumulate close to the ground, and they engulf communities, they engulf cities, towns, and countryside, and they can be there for several weeks. And you can imagine that breathing this air laden with particles and other gases, we're going to show you that later on, leads to problems, asthma problems, heart problems. Kids and elderly are most affected by the thousands and sometimes even hundreds of thousands of cases. What is burning most of the time, what is burning is peat. There are other soils in the forest that are flammable because they are rich in soil, in carbon. But the most abundant one is peat. Peat is the natural decomposition of vegetation that doesn't get oxidized, and it degrades very, very, very slowly, and it can actually be in the soil from thousands to hundreds of thousands of years. So it actually is a way for nature to store carbon. If these peatlands, they get buried and they go deep in the underground, they actually end up over millions of years being gas, coal, and oil. So the oil of today, the hydrocarbons, fossil hydrocarbons of today, is the peat of millions of years ago. But we have peatlands in the world today. There are typical two belts of peatlands. One is the tropical belt. The most famous one probably is Indonesia, but there are other ones in Africa, tropical areas, and South America, and the boreal belt, which is particularly large in Canada, north of the United States, and Siberia. You can see that in the map over there, the green areas. And these are where some of the largest fires happen. So peat is rich in carbon, is in excess of between 12 to actually up to 56, maybe 60% of carbon of its content is a sponge, is a porous media. It means that actually it can sustain water. Sometimes it can sustain a lot of water. It can be flooded, and actually it can have more weight in water than it actually has in solid. And there is a point in between being completely flooded and being completely dry that actually smoldering can start to happen. Obviously, if it's very dry, it can smolder, but there is also a significant amount of moisture that is still can burn. And that's something that scientists studying the smoldering are fascinated by, which is to find the critical moisture content below which the peat becomes a peat. This particular peat under the study becomes flammable. Then strange things are happening. we knew of smoldering for many decades, not with this name maybe. The name is catching, scientifically speaking, over the last 20 years. But we are starting to see very strange smoldering fires. For example, the ones that are happening in the Arctic. The Arctic is very cold. Vegetation doesn't grow fast at all, but it doesn't degrade either. And it's so cold that it's very difficult for the ignition sources to initiate a fire. And then you could have an ice layer or a snow layer in some seasons. We are starting to see these strange fires that are happening far away. They are mostly because of lighting activity, and they're not only burning the little vegetation of the Arctic. Very often, actually, they go underground and they burn the peat equivalent of the Arctic. They sometimes don't call it peat anymore because it's frozen, and it's a type of soil that is permafrost. It's perpetually frozen, but it's rich in organic content and therefore is flammable. And we have seen them smolder. And it's a very strange behavior because there is no one there to detect them. There is no one there to suppress them. And they start to burn for many months. One of the behaviors that are attracting an incredible amount of attention right now as we speak is a type of smoldering fires. These are actually worth the cover of Nature and Science. This is, as a topic of fire science, is that hot that if you get a paper on this, you can actually go to Nature, not us. We're interested in contributing to other fields, but it's what is called zombie fires or overwinter wildfires. So I'll show you this sketch that we have here. So imagine that you have in the summer months, the vegetation is warm, there is no snow, it is cold, but there is possibility for having a wildfire with flames of burning vegetation on the top. But then at the end of the summer, because of suppression, because of rain, because of burnout, then the flames extinguish. But sometimes the soil is flammable and it starts to continue developing smoldering wise. It has been a transition from flaming to smoldering. That is the end of flames leading to the beginning of smoldering. I'm already contributing to explain the title. But these fires, these smoldering fires, can actually burn very slowly and continue burning in the underground for many weeks, as I've referred to before. It can actually even survive having a layer of snow on the top, as long as enough tiny little bits of oxygen can actually go through the snow layer, which is possible. Then these fires will not be extinguished. Might not spread or might not spread fast, but they don't get extinguished. And then when the spring comes and the layer of snow melts, then the fires can actually come back and ignite flames in the same place where they were in the previous summer. And that would be a transition from smoldering to flaming. That will be the beginning of flames. So in these fires, these overwinter fires, because they survive the winter, or these zombie fires, because people thought they were dead and they're coming back alive. It's a very pictorial name. They are actually showing the title that I gave of they are the beginning of flames and they are also the end of flames, and they create a continuous loop that could continue actually burning for even, it's a mechanism for having a multi-year fire in principle, and there is a lot of interest in studying these fires. Smoldering is also present in two other topics that I want to highlight. I've already told you about peat fires. There is another one, it's called residual burning. Is probably one of the most widespread types of smoldering that happens. This is when the flames, after the flame, the flames have been burning the vegetation, the grass, the shrubs, the trees. And after the flames die out, the humus layer, or maybe the vegetation on the surface or the soil, continues burning, smoldering. That will be a transition from flaming to smoldering again. And these fires we know are very important. We know, this is not new, that most of the emissions actually, and most of the fuel that is consumed in a wildfire, very often, more than 50% can actually come from this phase, this smoldering phase, and is given the name of residual burning. I just don't like the name residual burning because it's pejorative. It almost invites you to think, well, the fire is over, it's just a little bit of a smoke. But it is not just a little bit of the smoke if it is more than 50% of the emissions and the fuel that is consumed in a wildfire. So I recognize scientifically the meaning of residual burning. I will just love to be called smoldering, for example. And another one topic that where smoldering is not often mentioned, but it is in our community of fire engineers, is fire burns. Fire burns and embers that are burning, they typically land and they are smoldering. You can see in this photo, this glowing. Glowing is a particular type of smoldering that is so intense that you can see it because it emits its own light. It doesn't have to emit light in order to smolder. So they arrive smoldering, and they typically, when they start a fire in a structure or in a surrounding vegetation, they typically start first a smoldering fire that then transitions to flaming. So that will be the beginning of flames. Yeah. This is a close-up into the residual burning that I mentioned to you. I just want to highlight how different is the chemistry and the emissions of each of these fires. The flaming over here is propagating forward in this direction and is leaving behind this char area. The char is smoking. That's because there's smoldering happening. You don't see it glow, but it is smoldering. You don't have to see it smoldering to be there. And the flames, for example, will produce char. They will actually char the vegetation and leave it behind as the black color. And in the gas phase, they will release typically CO2 and soot. Soot being a very important type of chemistry, a chemical species in flames that gives it this orange color. It's very important in radiation, and its chemistry is fascinating. And CO2, because being more intense type of combustion, more complete, it is able to oxidize all the carbon in the hydrocarbon, mostly into CO2, although there is also traces of CO and other gases. But then the smoldering that is left behind, there is a transition from flaming to smoldering. It actually consumes the char that the flame had produced. So you will see that where the smoldering has been the strongest, there is no black spots anymore. They're white from the ash because smoldering has oxidized fully the char that was left behind. And the emissions that it produces is very typical of incomplete combustion. So there will be a lot of CO. There will be also CO2, but there will be larger amounts of CO2, indicating the combustion process is not strong enough and complete. There will be a lot of PEH. There will be a lot of particles being behind. So not only smoldering consumes a very large amount of fuel, it actually has a much larger yield of nasty species in the gas, like CO or particle matter and other toxicants that appear. So netly not good at all, despite the pejorative name of residual burning. In the context of fire burns, I want to show you this graph that I like it a lot. It comes from the group in Berkeley, where I study with Sarah. Is an experiment where they had a small wind tunnel and they had a fuel bed that could smolder with just pine needles and dust of cellulose. And they were dropping on it little metal balls that were hot at a high temperature. And they were reporting what was the temperature of the ember, of the metal ember, and what was the diameter of the metal ember. And when they were finding the smoldering ignition above this line, and when they were finding the flaming ignition above this line. So this is the flaming ignition, and this is the smoldering ignition, which already indicates very clearly that you can have ignition, the smoldering ignition, with spheres that are colder and they are smaller. Whereas to have flaming ignition, you need spheres that are hotter and they are bigger, which netly it is clearly indicating. And the difference between the transition, I mean, the smoldering, the flaming ignition and the smoldering ignition is significant. It is tell you it is much easier to initiate the smoldering and is much harder to initiate flaming. So that's an essential part of smoldering, that is easier to initiate than flaming. The work of the two of the organizers of this seminar series of LOF&BE, Sam Mancello and Sayaka Suzuki, they are very, very well known for the amazing work on ember ignition. And they also have reports which are very valuable on the difference between the smoldering ignition and the flaming ignition. Once smoldering keeps going, I'm just highlighting in a case where it's burning the soil. I want to make this sketch comparison. You can see when the vegetation is flaming, you have the bright radiative color with its own light of the flames, and the plume, which is typically darker and is very buoyant, it's very high temperature. So in the presence of the atmosphere, sorry, of gravity, as it happens on Earth, it goes upwards, and the plume goes upwards typically. Whereas what happens in smoldering, as I mentioned before, is you are burning the soil. The soil itself is what is being consumed. So it actually leaves behind a hole, a small hole or a massive hole. It leaves ash that typically is not that much present when you have flaming, but smoldering leaves a significant amount of ash, all of it. And the smoke is not dark and buoyant. It is light, yellowish and whitish, light color, and it's not buoyant. It doesn't go up. It goes laterally and stays attached to the ground because it's not hot enough. The smoldering process is not as thermally efficient and chemically efficient as flaming. So these are two very different types of fires. And already from far away, you can sense how much of smoldering and how much of flaming are happening. All wildfires in the world, actually all building fires as well, have a presence of smoldering and a presence of flaming. And different types of behavior have more one or the other. In terms of safety, we always are more concerned about flames. They move faster and they kill people faster. And rightly so, for safety reasons, we have our attention into the flames. But the smoldering, in modern terms, in damage to the ecosystem, in damage to in terms of emissions, and damage to climate change and links to climate change, the smoldering is gaining an incredible amount of attention because we see that it has effects in all these topics. So putting things together, I already discussed that smoldering is easier to be initiated, not only because you need smaller heat sources like small embers, or you need smaller heat fluxes to initiate it. It's actually even possible to initiate smoldering without an ignition source. This is because of self-heating. You just need a pile of the material to be a warm temperature in a very large amount of a big pile, and it's possible to self-heat and have smoldering initiated that maybe later on will transition to flaming without any ignition source, without an accident, without an arsonist. So it is that type of mechanism that would not happen in flames, for example. And also we saw from our own experiments and from the literature that once smoldering is going, it's actually more difficult to suppress. It requires a significant amount of water more than if it were to be flaming. We need at least 50% more of water per mass of fuel that is burning. If we were to smother it by lowering the oxygen concentration, which is done, for example, to protect libraries, we need to lower the concentration even lower than if we want to stop a flame. And if we want to hold these low temperatures such that the smoldering disappears, we will need to keep this holding, we will need to hold this lower concentration for months. Whereas if we want to stop the flames, we just need to do it for minutes. So easier to initiate, more difficult to suppress. We conclude that smoldering is the most consistent, the most persistent type of combustion on Earth. Indeed, if we look into all of the old fires that have been continuously burning and they are still active today, all of them are smoldering. The record goes to the Burning Mountain near Sydney in Australia, that is now a national park. And before that, it was a sacred site for the indigenous people that has been burning at least for the last 6,000 years. And there is evidence that might have been burning for 500,000 years. So it's a very old, continuously burning, smoldering fire of a natural coal seam that got exposed and at some point got ignited by lightning strike or maybe self-heating. And it has been burning for a very long time. And it's a fascinating visit. If you are at some point close to Sydney, you should go. And I can tell you if you want what you can look at, because if you don't know what to look for, it's strange. But if you know what to look for, it's fascinating. Now I want to show you something that we do in the lab. This is not something that happens in the field. This is how we try to understand smoldering. Because we run the hypothesis as engineers and scientists that if we understand what we're dealing with, if we understand the physics, the thermofluids, the chemistry of what we're dealing with, we probably can help solutions that are tailored to it technologically more successful. So this is a video of one of our experiments as seen from the top. This is a tray. The tray is about less than half a meter long. We are seeing from the top. Here you have the visual and here you have the infrared. And it's accelerated 600 times because this experiment took 4 hours. It's smoldering in reality spreads very slowly. It's creeping. You think when you are there a few minutes, you are absolutely sure that nothing is happening. But if you come back after an hour, you're surprised to see that now the black stain or the white stain, the black is the charring and the white is the ashing. is spreading and spreading, and you can see the heat and you can see the smoke continually happening for hours and hours. So the typical temperature of a smoldering is much lower. Instead of being in the order of 1,500 Celsius for the flame, it's in the order of 600, 700, 800 Celsius. The amount of energy that is released per amount of fuel that is consumed is very low, because smoldering is not thermally efficient. It's not a good combustion process, it's a poor combustion process. And the result of low temperature and low amount of heat release is that it propagates very slowly. We're talking about millimeters per minute, whereas flames propagate meters per minute. One way to explain both of them at the same time, both flaming and smoldering, is to look into the chemistry. Smoldering and flaming have a lot in common. Both of them are burning the same fuel. Both of them are converting the fuel and recombining it and producing smoke and heat. So they share a lot, but they're different, very different in the chemistry. For example, both of them have in common a pyrolysis step. This is a type of chemical step where biomass, in the presence of heat, solid biomass, in the presence of heat, splits into a gas we call pyrolysate, which is nasty, and char, which is solid. Everybody's familiar with char. And this step, as I said, it requires energy, so it's endothermic. And then that's part of the fire, but that's not the fire itself, because so far it has not released heat. Now, smoldering is when, of the two products of pyrolysis, when the char, which is carbon, is highly concentrated carbon in the solid phase, when the char oxidizes with the surrounding oxygen, then it actually leads to a type of combustion, which is smoldering. It happens on the surface of the char, and it is as combining solid and a gas. And that's typical of a smoldering, which is heterogeneous combustion. And it leads to carbon, water, and a very long tail of emissions and ash. Whereas in flaming, what happens is that is the pyrolysate produced in the gas phase by the biomass decomposition that recombines with the gas, oxygen gas in the atmosphere, and that leads to a flame, which also leads to CO2 and water and other emissions. So what they have in common, smoldering and flaming, is the pyrolysis step, and what they have in difference is that the smoldering is oxidizing the char, whereas flaming is oxidizing the pyrolysate. Indeed, we had an experiment where we look into the role of the char. For example, we did experiments very similar to the one that I showed you animated before, where we explore the fact that char, combining these two reactions, is an intermediate species, because at the beginning you only have biomass, and at the end you only have ash, gases, and water. So but in between there was this species char, that it was produced by the first reaction and it was consumed by the second reaction. So in chemical kinetics, we like doing these distinctions. So we did an experiment where we were, there's a circular tray in this case, of peat, and we ignited on the top with heat, and the smoldering started to happen in the tray. This is, for example, a particular snapshot. You can see that actually it was with infrared, it was burning and it was smoldering. And we were stopping the experiment at different time steps and repeating the experiment again. And we were literally opening the bed and separating the white from the black. We were separating the ash from the char. And when we put everything together, we have a normalized amount of mass and time. And what you can see is the amount of char that we were seeing, well, the amount of peat that we were seeing in the sample, it was going down very quickly. And there was a point after 15 minutes that there was no peat left in the sample. The reaction continued and the smoldering happened, but the peat had disappeared. Whereas when we were tracking the amount of char, what we were saying is that char was always going up until it reached about 20 minutes. And then after 20 minutes, the amount of char started to decrease. So at the beginning of the fire, there was only peat. And at the end of the fire, there was mostly just ash and very little char. In between, but we had a process where the peat had been converted through pyrolysis into char and pyrolysates, and then the char was oxidizing with heterogeneous combustion and leading to the smoldering process. One important thing is how smoldering starts, right? Smoldering could start by self-heating ignition, or it could be by itself through a thermal event, or actually it could be that a small flaming ceases, the end of the flame ceases, and then it leads to smoldering. When we put things together regarding the conditions that lead to initiation of a smoldering, we recognize, thanks to the pioneering work of Franzen in the 90s, that the single most important property of the soil, of the peat, is its moisture content, the amount of water that goes inside this porous media. This is expressed here as percentage over the dry mass. So that's why it can go up to 200. 200%, for example, it means that it has 2 times more water than it actually has solid. Or for example, 50% is just that, no, there is just a 50% increase in the weight of the solid that is due to water. And the other second variable that we know is very important is the inorganic content. You can split the amount of content in peat as the amount of water, the amount of carbon, or the amount of organic is called, and the amount of inorganic. So inorganic content is the content that cannot burn. It's solid, is the mineral, is the one that would lead to ash when it burns. And we know that if soil is very rich in organic content, it can't not burn. Or if it's very low in organic content, it will burn. And when we put everything together, thanks to Franzen through experiments, the dots in black, and as through computer modeling, the cloud that we have here in orange, what we recognize is that there is a split of this domain where if the sample is too inorganic or too wet, it can't not burn. So it cannot burn. Or there is another realm where if the peat is low in inorganic content, mainly that is rich in carbon, or is dry, it actually can burn. And then you have in between, you have the criticality. So this is a very important thing, for example, when you're trying to identify if the peatland is vulnerable to fire. If you have a forested area in top of a peatland, and there is a fire in the Arctic, in the boreal, or in the tropics, and you want to know if you're concerned about smoldering, the first thing that you would do is to estimate the moisture content of the peat. And if it's, for example, if it's a peatland that it has 40% inorganic or 60% organic, and it has more than 100% moisture, then you are probably safe, and it will be very little ignition hotspots, just a few of them. But if it's 20% inorganic and 80% organic, and it's 50% of moisture, then you probably will see an incredible amount of hotspots, and probably you will have very large smoldering fire. So that's why drought conditions are such an important event for smoldering, and why carbon-rich peatlands are also very important. Now I want to continue telling you things about smoldering, but wrap up around what we consider challenges, 4 top challenges that we have found. The first challenge is that smoldering is multidimensional process. It's actually 3-dimensional because it happens in the soil, and it has a component that is lateral, that is horizontal, that we call the horizontal spread, and it has another component which is vertical, that goes into the soil. And the 2 of them are significantly different. The 2 of them are governed by different mechanisms of heat transfer and oxygen arrival, and the 2 of them have different speeds, and the 2 of them have a different dependency on moisture, density, porosity, and inorganic content. And they need to be, the 2 of them are very important. For example, the lateral one will give you how much a hotspot is growing in time, which is what you will see from the satellite, the hotspots growing. And the depth gives you how much actually is the footprint in terms of carbon and emissions, because it is the depth of the soil that is so dramatic in its amount of fuel that it can burn. This soil is a very dense amount of fuel compared to the density, overall density of vegetation. To the point that, for example, we have discovered, and this at the beginning became controversial. We even thought that we had the experiment wrong. And then we also thought that we had the model wrong, but actually we realized that it was not wrong, that it's just that fascinating, where we see an acceleration of the vertical spread rate with moisture. So although typically in all fires known to us, as you increase the amount of water, you are making the spread more difficult because there is more water, there is more energy that has to go into evaporating it. The vertical spread of smoldering has the peculiarity that the more water it finds, there is a range. This is moisture content, and this is the spread rate dash. That as the soil is hotter, wetter, but it ignites. So it's more wet, but it's still below the critical value. So you can ignite it. They actually will propagate in depth faster. Because it is true that it has more water that has to evaporate, but once it evaporates it finds a soil that has lower density, because the water has been taking space, and now it is being evaporated, and suddenly the fire can propagate faster. So it's not faster because it has a higher heat release rate. It is faster because it's able to move across the pores that are empty faster. Fascinating, now published in many different sets of experiments and models. Another peculiarity of the multi-dimensional spread of smoldering is what is called the overhang. The overhang, people in the field were fascinated by it, is when smoldering goes under. And instead of burning right at the top of the surface, it becomes shy because of heat losses. Smoldering is weak combustion, so it's very sensitive to heat losses. So it prefers to vary itself a little bit and continues burning. So it creates an overhang. This overhang can be a few centimeters, or it could be actually a meter. And the overhang will break because at some point the soil has lost its strength. It will break and it will actually fall inside the fire, and it will be suddenly an impulse of a smoke and more fire happening, and another overhang will be formed. So overhang is very typical of smoldering. And at the beginning, people thought, geoscientists, that would happen, which they know a lot about soil density. They thought, well, the overhang is because the soil at the top is higher density than the soil at the bottom. And that's what they thought it was. And we actually, until we were able to replicate overhang phenomena in the lab, and we realized that it's because smoldering finds it faster to propagate a little bit below, protected. The overhang protects it from the wind. It still arrives with oxygen, but the heat losses are lower, and then it's a little bit faster, a few centimeters inside. Then we also have the multidimensional when we go into the field scale. When we look into the field, fires that you can actually look at the satellite, not just this image over here where you have the helicopter trying to fight a smoldering fire, and they're trying, I think it was in New Zealand, they were trying to flood all this area that has been smoldering for several weeks. We're talking about even bigger fires that might happen in Southeast Asia. You have an image here, for example, of a fire that lasted for almost 200 days. It started with hotspots. The yellow one are hotspots, smoldering hotspots. And over the course of all these days, it started to grow and the hotspot started to merge. So for example, this is something that is definitely multidimensional because there is a lot of two-dimensional spread as you see hotspots creating and merging, and then you have the in-depth that the satellite cannot see, which leads to a dramatic amount of emissions. And for example, we simulate this with models that we develop because the scale of them, we find that cellular automata is very convenient for speed, and actually with the right physics, it gives very meaningful simulations. Second challenge, which I've already highlighted to you, is the transition from smoldering to flaming. This is a topic, and I took this from my supervisor, Carlos Fernández Pello, that remains fundamental combustion science, absolutely fascinating, coupling of chemistry at the highest level with multiple steps and very complex chemistry of pyrolysis and oxidation in the gas phase and in the solid, and thermofluids, and it requires very detailed experiments, and it requires models, and unfortunately all this is lacking, so we are not able to understand nor to predict when smoldering will transition to flaming. It's a very famous set of images. It's not peat, it's polyurethane foam. This polyurethane foam had been ignited at the bottom. The smoldering has been propagating upwards. You can see the char marks over the course of an hour, and then within the course of a few seconds transitions to flaming, and the whole sample is engulfed, and the sample is gone within 10 seconds, whereas before it was going to be there for several hours. So the dramatic difference between flaming and smoldering, but in this case, the flaming was actually a transition from smoldering. So no one would be able to understand, for example, this type of phenomena if they think that the flame was there since the beginning. It will not match the evidence. Whereas you sometimes have to realize that there could be a smoldering event that changes completely the spread rates, the behavior, the signatures, the emissions. And this is the other transition. Sorry, this is the transition for smoldering to flaming that I mentioned to you before. That could happen actually very similar to happening in zombie fires. Looking into what we know from the transition from smoldering to flaming, we know, for example, the air velocity is very important. This is as you increase the air velocity. These two lines over here is the transition to flaming in the trailing edge, and these are the transitions to flaming in the leading edge, and this is the transition to flaming in the trailing edge. And you can see that here at high velocities of the wind, you have transition. Here at high velocities of the wind, you have transition, but at low velocities of the wind, there is no transition. There is only smoldering. So we know, for example, that in order to have transition, you need a significant wind. The value specific of the wind changes with a specific setup, but you need wind. The wind promotes the transition to flaming. The third one is very modern as well, is related to the emissions that are coming from smoldering. Smoldering, as I told you before, is incomplete type of combustion, so the chemistry is always more complex in the gas and in the particles, way more complex. than flaming. And flaming is already quite complex. The topic of emissions from flames, even in a combustion engine, in a fire, or in a wildfire, it is a fascinating topic that has kept scientists busy for many, many decades. Well, imagine all then that remains to understand the emissions from smoldering, because it's even more complex, and we have done as a community much less. So there is a lot to go forward. This is just one example of the yields that we found in some of the experiments that we did. You can see, for example, there is a significant amount of CO2 coming from smoldering, which is true, but there is a significant amount of CO2 or CO, sorry, which is unusual. For example, in flames, you will have a much lower ratio of CO to CO2 in flames. You can see here, this at the bottom. This is time in the experiment. This is the cumulative CO to CO2 ratio, and you can see that for smoldering of the same fuel is very high, it's in the order of 0.4, whereas for flaming it's much lower, it's in the order of 0.1, maybe peaking at 0.2. This image over here shows you the importance of emissions. This is the beautiful Marina Bay in Singapore. I love it. It's a beautiful city and a special place there. And this is the Marina Bay when there is haze. Haze in Singapore often happens about every 3 years. Sometimes it lasts for weeks, sometimes it lasts for months. And you can see how dramatic is the difference. This is not a fog, and this is not that it was done at a different time of the day. These photos are because of the haze, the situation that happens in that city. Imagine that you are breathing that air, and this will go inside the houses, and you cannot escape because it's the air of the region. It's not just the air of a particular street. You can see, for example, the particle matter, the 2.5 particle matter, so it's smaller than 2.5 microns. These are the particle matter that doctors worry about tremendously. This is in red what happens in Singapore when there is haze, and this is in blue what happens in Singapore when there is no haze. So this blue one, you could say, well, that's because of the cars. This could be because maybe there is a little bit of particle matter coming from the sea, from the ships, from the airplanes, very small. Singapore is considered to be a very clean city, but that actually changes tremendously when there is haze. And typically the haze is not the fault of Singapore directly. It is because of fires that are happening in Indonesia or in Malaysia or other parts of Southeast Asia. When we look into the emissions, as I said before, there's carbon dioxide. This is not just a specific experiment. This is actually what the literature, when we put everything together, says. The N is the number of the studies that have reported these values. These are yields, so grams of this gas per kilogram of fuel that burn. You can see that everybody agrees that is carbon dioxide, the one is emitted the most, followed very closely by carbon monoxide in very large amounts compared to other types of combustion. And there is a significant amount of methane and other hydrocarbons that are coming afterwards. And you can see the difference if it's a boreal fire or it's a tropical fire. It's slightly, not really significant, but there is typically more yields in the tropical fires than there are in the boreal regions. We can look into the same for particle matter. There is a very wide amount of different particles in form, in chemical composition, in size, and this is a topic that has hardly been touched. Maybe there is no more than 50 papers on the particles coming from smoldering, whereas we would need about 50,000. So imagine how fruitful this topic is. We can see, for example, there is a significant amount of particle matter 2.5. There's significant amounts of organic carbon, which is a type of carbon that leads to more complexity, or even elemental carbon, which is soot, which happens in much larger amounts in smoldering, or actually maybe it doesn't happen in smoldering, just a little bit of flaming that might happen in the field. And the type of carbon that happens in those molecules is significantly different than the constitution of particles in flaming. These are some of our samples, our filters. When we sample emissions, you can see already by the colors. This is when we sample flaming of PM1. This is flaming of between 1 and 2.5 microns, and this is when it's larger than 2.5 but lower than 10. And you can see the smoldering one is very different color, different types of emissions when we look into the chemical composition, or we scan with a microscope their shape and their size. Very, very different. And the fourth challenge, and with this I almost finished, is the links between smoldering combustion and smoldering wildfires and climate change. So I can start with carbon emissions, for example, in this mechanism that I'm going to describe to you. In blue are arrows of topics of science that I myself don't work on. So I am netly a learner, and I just read the work of others. And scientists, when there is an excess of carbon emissions in the atmosphere, that is leading to climate change, and climate change has multiple forms. But the ones that we worry the most is that it's increasing the temperature and is making soils drier. So if the soils are drier and they're warmer, I now can tell you from our experiments and models that then ignition and self-heating will increase. So we will have more wildfires and larger wildfires that will consume more soil and more emissions, and they will release more carbon into the atmosphere. This carbon that is released in the case of peat is ancient carbon, is definitely more than 10 years old, is hundreds, even thousands of years old, which means immediately, instantaneously, it becomes a net emission because it will take hundreds to thousands of years to grow, to store that carbon again. That means in the moment that it burns, it's become a net emission. And it creates a positive feedback mechanism where more emissions will lead to more fires that will lead to more emissions. Now, when we look into flaming fires, that's different. And I put it here onto the side because flaming fires are burning young fuels. They're not burning ancient carbon. They're burning vegetation, grass, which is definitely very young. It grows within the same year, or shrubs grow within 5 years, and some small trees or branches of a tree that grow within a few years. So when they burn, if we allow them to grow back again, the grasses, the bushes, and the branches, they will not have a positive mechanism. They will actually become carbon neutral. Except if we are burning very old trees, like is happening now in California, for example, or we don't allow the forest to grow back again. If we are burning old fuel, or we are not allowing it to grow again, then we are creating a positive mechanism. But for smoldering, we don't have a if or a condition. Instantaneously, when peat burns, it becomes a carbon emission, creating a feedback positive mechanism. So the way we have approached these 4 topics is in the lab and doing experiments. We are engineers, many of you know us, and actually many of you use the same approach. We are all familiar with this, but we did something unusual. As engineers, we don't do field trips. So we by working with a lot of your scientists, we realized they do field trips. So we should do field trips and we should learn a lot from these experiments. So we did something unusual. It's not that we went into the field and observed a fire that someone else had created. We did an experiment in the field. We actually started our own fire because as experimentalists, we wanted to capture the size, but we wanted to have an experiment. We wanted to know how it ignited, how was the field before, and to monitor the experiment afterwards. So we did these experiments in Indonesia in a real peatland. This is what we did. This is our lab. It was there for 3 weeks. And each of these plots was subdivided, and each of these plots become an experiment of their own, burning for some of them for a few days, some of them for several weeks. And we study the ignition, we study the spread, we study the effect of day and night. Obviously, this was in Indonesia, so it rained naturally, an incredible amount of rain on top of us. We studied for the first time how smoldering can survive the rain. And then before leaving, we were very thankful to our host in Indonesia. We make sure we suppress it, right? We didn't want to leave this with a fire behind. We will end up in the news for the wrong reasons. So we had to suppress it, and we spent 3 days suppressing the fires to make sure that we were not leaving anything behind. And we learned from that as well. And we have these multiple papers on ignition, spread, emission, and suppression of what we did here in 2018 before the pandemic. This is the gumboot experiment that we did in the field. And this is all the things that we did. We had a lot of fun, and we came back and we survived it being in the jungle. Highly recommend it to any of you that wants to do it. It's not just going to the field, it's doing an experiment in the field. So the geoscientists that were with us to make sure that we were alive, they found it fascinating that we were doing an experiment, not just observing a natural phenomenon. And the engineers in us, we were fascinated that we were in the field. There was no power cords, there was no bathrooms, there was no a cafe to sit down. It was fascinating. Good. So with this, I finished just to hopefully I've passed you to use some of the interest and the passion that we have for smoldering. We've been studying smoldering for 20 years. That this is something that happens in the forest, in the peatlands, in the Arctic, that is burning the soil itself, that very often is called residual burning, and that is also related to firebrands and embers. That the top challenges that we have identified that continue being challenges, which as a positive, right? Challenges as researchers, we like challenges in the sense that these are topics that are far from being finished, that hardly have been touched, is the multidimensional spread of smoldering fires, the transition to flaming, the emissions, and the feedback mechanisms to climate change. So with this, I finish just highlighting that I do think that smoldering combustion is an emerging scientific topic, and it requires a lot of attention and a lot of help. And with this, I finish. Thank you very much.
Thank you, Guillermo, for yet another awesome talk. I completely agree on how important smoldering is, because, you know, especially in wildland fire, like that transition from smoldering to flaming, like literally happens like every day on every fire, right?
Yes.
So, I mean, every night it dies down and smolders, and then every afternoon it picks back up in flames. So, you know, it's a critical piece to the puzzle to understand. I mean, yeah, fires and buildings too. So,
But so, Sarah, this is fascinating. So you mean that very often the flames die at night?
mhm.
Okay.
Yeah,
Because it's
it'll
difficult to
often,
fight fires at night, but because they don't see and it's dangerous. But okay, I didn't know
yeah,
it was happening that frequently.
yep. I mean, it's not like they could completely, like, all the flames go out at night. But
Yeah, no, but they significantly go down. Yeah.
they significantly go down at night, right? Often, a lot of firefighters actually rely on it, right? Is that the temperature's cool, the humidity's come up, usually the wind dies down, the fire behavior like really like lax at night, and then, you know, come 2 or 3 in the afternoon the next day, then it picks back up. So, like there's a big difference between night fire spread, daytime fire spread usually, and smoldering plays a big role in it, in the nighttime spread for sure.
Okay.
Especially, I mean, like you get a log, you know, a big log is not going to burn in flaming very easily. So that's going to transition back and forth all the time. So yeah, I will give people a chance to type questions in the chat box, or if you're comfortable with it, go ahead and unmute and ask them yourself. I have plenty.
If there are questions in the chat, can you read them,
yes,
Sarah, so I don't have to?
So one just popped up from Christos. So he thanks you for the presentation, and asks, in a smoldering fire, does the wind affect the horizontal and vertical rate of spread?
Actually, that's a very good question. Yes, the wind affects both the horizontal and the vertical spread. Much more the horizontal one. The horizontal one is very sensitive to wind, not as much as flames, but it's sensitive to wind. It actually leads to transition to flaming as well. And the vertical, it is enhanced by the arrival of air because it brings more oxygen. And typically, smoldering is always starved continuously by oxygen, so it can consume more than it arrives. So wind also makes the in-depth spread, the vertical spread faster.
Is there a limit to that? I mean, as it burns in depth, right, you're going to get an ash layer on top that'll insulate.
Yeah, there is a point where if the wind is blowing too much, it starts, instead of helping, it starts to not help. Actually starts to remove the fuel itself. Sometimes actually the peat itself starts to fly away. The char might fly away, or the flame might have, so not the flame, the smoldering might actually have difficulties because it's losing so much heat. But that will require very strong winds to reach that point.
Gotcha. I see somebody else is typing, so there might be another question coming. I'll ask one of mine. So you mentioned this coal seam that's burning for 6,000 years in Australia. What evidence are they using to piece that together, to date it?
Yeah, so it's fascinating, Sarah. Seriously, all of it. You have to go. I'll go with you. So the geologists are able to track the disappearance of the coal. So literally what leaves behind is it leaves a massive hole that it has collapsed. So that's because the coal seam has disappeared, right? And they can also identify that the rocks and the stones have been heated up and broken. And they can follow that trail very slowly. And I think they can trail it by a kilometer. I don't know how much it is. It's very long. It's a straight line kilometer. It's the coal seam. And they know the average spread rate of the fire because this fire is known since 1865. So we know where the fire was in 1865, and every single year, a lot of tourists, well, not tourists, but a lot of English people, British people, when they arrive into Australia, they were sometimes going and visit this fire. They thought it was a volcano at the beginning. So we have good records of where the fire was, and then they backtrack it, and they say, well, it's at least 6,000 years, at least. There is very strong evidence for this. And then there is more evidence that maybe actually the coal seam had burned more than 1 kilometer, maybe 6 kilometers in the other direction. And that's the one that says maybe the fire has been burning for 500,000 years.
Okay, so they're not like doing.
Not
isotope dating or something on it, or I don't know.
Not yet, not yet. I mean, the sad thing, I mean, obviously I have a bias, is this virus beyond fascinating. It's a national park now. It's a sacred site. It is scientifically speaking absolutely fascinating. There is like 2 papers, scientific papers on it. And the 2 of them are from the 60s.
Wow.
I mean, I would love to get myself funded to go there and do a field trip and take samples and do infrared and do predictions. I will be fascinated. One day.
That's pretty awesome.
I mean, someone needs to do it, Sarah. So someone has to do it.
Agreed. Yeah, work on finding the funding. I still see somebody's typing, but another question has not come up yet. I have 2 minutes. Oh, there it goes. So thank you for the presentation. And they're working on a simulation of haze trajectory using high split from peatland fire. How to determine the emission rate in different types of peatland and also different depth of peatland, which is a good question. And what are the factors or parameters to be included in calculating emission rates from the peatland?
Yeah, so first is to get the whole of emission factors. So emissions factor is how much of different gases and different particles is emitted per mass of fuel that burns. And there is a literature review on the topic, and there are several papers of different peat types and different conditions. So the first thing is the emissions factors. Once you have the emissions factors, now you have to figure out how much was burning, which means that you need the surface area and the evolution of the surface area. We call the hotspots. So you need to know how many hotspots and how fast the hotspots were growing. That's the surface area, but that's not enough. The satellite can help you with that because you need to get the most difficult one, which is the depth of a spread. The satellite will not be able to help you with this. So typically what we do is maybe someone has done a field site and maybe has taken photos with an inclination, and you can measure or estimate the depth, or maybe someone has gone and measure with a stick the depth. And if you don't have that, what you can do is you can go into literature, which what we did, and we reported different depths of depth of burn. It's called depth of burn that have been reported in the studies with average and standard deviation. And then from this combination, yields, surface area, and depth of burn, then you can actually make an estimation of the plume volume that is being released, and then maybe you can track it and see how it moves with the wind.
A lot of unknowns in that one. One other question finally popped up. I'm going to ask one more because we started a little late. Again, thank you for the presentation. And about the vertical spread, is there any threshold in thickness for smoldering? We would assume that the oxygen is barely available after a certain thickness of soil. And what about the effect of released gases or particles in prevention in reaching the oxygen in depth, like the flow up?
Yeah, so if a smoldering starts from the top, which is by far the most typical scenario, then the smoldering itself is removing the soil, and it can go downwards indefinitely as long as there is fuel and as long as the soil is not too wet. And what I mean indefinitely, we have seen this. There are fires, smoldering fires that are burning for many, many years. But if it runs out of fuel, then because it reached the mineral layer, for example, it will stop there. Or if it finds the water table because the water table is there, or the water table is growing, maybe it's going up because it's raining, or some of the firefighters are reflooding, then when it reaches the water table, then it reaches a speed that is too wet and it stops. But if these 2 critical conditions are not met, there is fuel and is not too wet, then it will go indefinitely. If it ignites on the top, because it itself is creating a hole. Now, if you ignite from the bottom, which is possible, then it has to propagate against the soil. It's the scenario that was mentioned. Then there is a critical thickness. But it actually, what it means is that the thicker the soil that is between the oxygen and the bottom ignition, it means that the spread is slower. And there are experiments, fascinating experiments from the 50s, that report smoldering going across a pile of a meter over the course of 2 weeks. So they ignited, and they saw the fire coming up at the top of the pile 2 weeks later. So it requires a lot of patience to do these things.
Oh boy, does it.
Oh, it's amazing. That paper is amazing.
Huh, crazy. So I said that was going to be the last one, but another really good question just popped up that I'm going to make you answer real quick. So what factors are influencing the transition to flaming? Obviously, we see wind influencing reflaming in coarse fuels such as logs, but is it just wind and fuel moisture and possibly fuel density? And will we ever be able to predict the transition and therefore be able to understand our spreading wildfires better?
Yeah, so I am absolutely convinced that we will end up understanding well transition to flaming. I don't know when, and I hope to be alive by the time that happens. It is obvious that that would happen as soon as the community starts to study transition to flaming in a scientific way. There is very little research going on the transition to flaming. This is what I chose as topic number 2. It is a fundamental combustion process, so it's hardcore science. It's not easy science, it's hardcore science, and it is really important. The transition from smoldering to flaming, I think I have tried to make the point. So if it's difficult scientifically speaking, it's challenging, and it's important and relevant, this should be calling for more scientists. But they're coming, but just slowly. So I am convinced at which point we will know. So we know that the wind is, we know this from experiments. It's very difficult to simulate this experimentally. There is only one paper, sorry, it's very difficult to simulate this computationally. There is only one paper that simulates computationally the transition to flaming. One paper in the literature. And there is about 100 where we experiment. So most of our knowledge in the transition to flaming comes from experiments, small experiments. And we know wind has this very important role. We know that the moisture of the soil or the fuel itself is very important. We know that the orientation of the fuel is very important. It's not the same if it's horizontal or if actually upwards. We know that fuels that are upwards are preferred because they create the additional wind of buoyancy. So buoyancy helps the transition to flaming. We know that the porosity matters because if it's very porous, it allows the flow of air to go through it faster, and it allows the smoldering, the oxygen to go deeper. These are the characteristics that we know that matter. And we know very little. For example, I can tell you already, and we are research that we just finished, we have looked into what is the effect of not just having wind, but having wind that is pulsating. So not just a continuous wind with the fan at a given fixed velocity, but what if we purposely make the wind pulsate? And what we see is that it promotes the transition to flaming. It's actually, for us, a breakthrough. It makes transition to flaming tremendously repeatable. So instead, it removes the stochastic nature of transition to flaming. We are able to get a transition to flaming on the clock. We know it's like we know from the experiment that if we pulsate the wind at this wind quantity, we have transition in 3 minutes, and we repeat the experiment and we get transition in 3 minutes, which is something that I have not seen before. But it has to be pulsating. Now, the fascinating thing is, why does the pulsating nature matter so much to the transition to flaming? And people will have hypotheses. We have our own hypotheses. The hypotheses have to be tested. The hypotheses have to be researched deeper, the more numerical model. And this is one of the venues of scientific progress.
Well, awesome. On that great topic there, I think since we're out of time, I'll cut it off there. There is one other question in the chat box. If you want to go back and answer that offline, we can get that to you. But thank you, Guillermo, again, very much for such an awesome talk on an awesome topic. So stay tuned, everybody. We'll have another webinar in August, and we'll announce that shortly. So thank you, everyone, and I'll stop the recording at least. So
Thank you so much.
Thank you, Guillermo, for a great talk.